Hello everyone, welcome to the Prelab lecture video for acid-base extraction. Alright, this will be for CH4511 Organic 1 Lab. Alright, so in the acid-base extraction lab, here you can see on the front page of our experiment that we have two different bases, well the same base but two different concentrations of bases, two different concentrations of acid. We'll have an unknown mixture that we're going to separate. We also have an organic solvent called dichloromethane or DCM. Also, we have anhydrous sodium sulfate. This is used as a drying agent to remove any water from the dichloromethane solvent. All right, and so everything else is more or less glassware of some kind. But kind of getting into the meat and potatoes of what acid-base extraction is. Well, this technique comes in very handy when you have a complex set of compounds, right? So here, this table is actually a list of all possible unknowns that could be seen throughout this experiment. All right, and each one of these can be classified in one of three ways. You can either have an acidic compound, right? Especially if you see like acid at the end of it. I think that's a key indicator, right? But you notice that it has this carboxylic acid functional group, so this is an acidic compound, right? Same thing again, acidic compound, acidic compound, acidic compound. You also have basic compounds, and those are going to be characterized by having this amine, not amide, but this amine functionality, NH2. So here, 4-chloroaniline, 4-nitroaniline. Let's see. You've got this ethyl 4-aminobenzoate, para-toluidine, right? All of those are considered basic because they have that amine NH2 functional group. All right, and so the unknown that you would be working with is actually going to have two of these. It's either going to have an acid or a base, an acid and a neutral compound, or a base and a neutral compound. And so looking at our neutral ones, we have some options here like biphenyl, camphor, fluorine, naphthalene, phenanthrene, and yeah, trans-stilbene. All right, all of those are considered neutral. Oh, and anthracene right there, because none of those contain a functional group that is acidic, like donates a proton, or that is basic, accepts a proton. All right, so those are going to be our neutral class. So to kind of get into understanding what's going on here, imagine, I'm going to make this a little more complicated than the scenario that you have in lab. Imagine you have an unknown mixture and it has all three, or one of each of these three classes of compounds in it. It has a basic with the amine, it has an acidic compound with the carboxylic acid, and then it has a neutral compound. And yes, in case you're wondering, I just took top row, top row, top row. All right, so none of you will have an unknown mixture that has three different types of compounds in it. It's only going to have two. But I wanted you to kind of see what happens to each one of these as a separation would take place via our extraction method. All right, so to separate the three, we are going to utilize acid-base reactions. All right, and so first off, what we're going to do is we're going to take this mixture. It's just going to be a solid to you. It's going to be homogeneous. You're not going to be able to tell that it's three different compounds in it. So you're going to take this solid mixture and you are going to dissolve it in dichloromethane. All right, all of these are very large molecules. They have 6 or more carbons, and so they are not very soluble in water or any type of aqueous solvent individually. So, but all three of them will readily dissolve in these forms in DCM, in dichloromethane, and organic solvent. All right, so and then what you would see happen here is when we look at each one of these three, when we dissolve them in dichloromethane, we're going to actually put them in a separatory funnel. Here's a pretty good picture of what a separatory funnel sort of looks like. And so what you would do is you would pour in your solution. So you would have, right now you'd only have one layer. So let's say your bottom layer here would be the DCM, the dichloromethane, that contains the 3 dissolved compounds in it. Right? Then, in order to actually separate these, you need to add a second layer, an aqueous layer. All right, and so the aqueous layer in this regard is actually going to react with the one of the 3 molecules dissolved in DCM. So what we would see, for instance, is in our first step, if we took those 3 compounds, right? We have our aniline derivative, our carboxylic acid derivative, and our biphenyl. If we look at those, and let's say we take them dissolved in DCM, right here. So we have forgive my drawing, but we have our separatory funnel that has DCM with the 3 compounds dissolved in it, and then we add base, specifically sodium hydroxide. Right? When we do that, sodium hydroxide will be an aqueous base solvent, so it's in water. So oil and water don't mix, right? So that's kind of the same thing we see here. DCM is an organic solvent, not an aqueous solvent. So when you put these two together, they will separate from one another. You'll have 2 layers, right? And so here I've shown you you'll have a water layer, your aqueous layer, and then you'll have an organic layer, your DCM here. Now, when you add this aqueous base to the mix, it will selectively react with one of these 3 compounds, right? And so remember, amine here is a base. So a base and a base don't really react with each other readily. We're really not going to see a reaction take place here. So that's why I put here no reaction. So in essence, this amine-based molecule will still look like an amine-based molecule. Right. However, when we take that base and when it comes into contact with our acid, our carboxylic acid specifically, we can see one of the lone pairs on that hydroxide can attack this hydrogen to take it. Right. So this acid will donate a proton, so to speak, and then we'll turn this compound actually into a charged ionic species like this. And as you may recall from freshman chemistry, ionic compounds are readily soluble in water. They are highly soluble. So this did nothing, stays in DCM, right? Our amine functional group. Our acid functional group reacted with the base, turned into an ionic compound, and is now going to be more soluble in water, and thereby when we see these 2 layers, the amine functional group stayed in the DCM, but our ionic compound, our deprotonated acid, is going to migrate to the water. Now, it's not just going to move. You're actually going to be vigorously shaking this separatory funnel so that you can kind of like mix the 2 phases together temporarily, but they will separate quite readily over time. All right, and then of course our third compound is our neutral compound, the biphenyl. It's neutral. It doesn't have an acid or a base functional group associated with it, so no reaction will take place. So that biphenyl, just like the amine functional group, is going to stay in the DCM. So now you have actually separated these 2, right? You separated 1 from the 3. You've separated your acidic compound, and it's going to be in the water. And so with this being a separatory funnel, you just have what's called a stopcock right here, and you can spin it or twist it, and it'll allow the DCM to come out, right? And then you'll stop it before water starts to come out, and then you can bring in a second beaker and put the water or your aqueous solvent that contains this ion in it. Now, so what we've done so far is we've utilized acid-base reactions to separate one compound, right, this one right here, from the other 2. Right? However, these 2 are still together in DCM, and we want to separate them as well. Okay. Now, before I get to that, though, it says here, why is DCM on the bottom? Right? Why did I draw it on the bottom, and why did I draw the aqueous phase on the top? Well, a lot of that stems from understanding density, right? Or just knowing the density. And so when we look at DCM here, dichloromethane, which is the same thing as methylene chloride, it has a density of about 1.34, while water and saturated aqueous solvents tend to have a density of about 1.2. So since the DCM is more dense, right, it's heavier, it's going to be on the bottom. Okay, and so that's how we know when these would separate. So I don't want you to think that every time you use a separatory funnel that the water is going to be on the top and that the aqueous phase is on top and the organic phase is on the bottom. It depends on the densities of your two solvents. Okay, now one thing to also understand here in this reaction, yes, we are going to see that this ionic form of the acid is going to it's going to be much more soluble in water, but some of it could stay behind here, right? Could stay in our organic phase, and the reason behind that is something called the partition coefficient. And so, or kind of the chemical principle explaining this, the partition coefficient is pretty much trying to talk about how a solute would travel between two different solvents based off of solubility, right? So even though this guy right here is not very soluble in DCM, some of it's going to stay behind because it does have some solubility, right? When you go back and talk about KSP, right? KSP is equilibrium based off of solubility. And so, yes, some of it's going to be more soluble in water, but some of it will stay behind because you do have this equilibrium that can take place. And so what do you need to do to try and get as much of that acid out as possible? Well, you want to separate these two, go back to where you now just have the DCM, and add another amount of sodium hydroxide, shake, 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 get your two layers, separate the two, right? By letting them flow through the end here, separate the two, you'll have your organic, your aqueous, and then do it a third time. So the more you do it, the more of this deprotonated acid you're going to pull out of the DCM, okay, based off of partitioning. Okay, now, after that, like I said, once you've done that, you still have two compounds remaining. You have your amine compound and your neutral compound. So now, since amines are basic, you can add a strong acid like HCl and do another acid-base reaction. So you can see here the lone pair on the nitrogen is attacking the hydrogen of HCl. Right, so it's going to protonate the nitrogen, right? As we see here, we have NH3+. And so we have turned this neutral basic compound into a charged conjugate acid form, right? And so we have a positive nitrogen. It's an ion, which means ions, as we recall, are highly soluble in water. So now we can separate them here, right? So that's what we're kind of doing here via our separatory funnel view. We started with just DCM having the two remaining molecules. We added our acid. Right, the acid and the amine reacted with one another, and so it would migrate to the water, right? Because remember, acids are aqueous, so they, just like the base was before, these acids are going to be, HCl is going to be aqueous. It's going to have water in it mixed with it. So that's why I put water here, but technically we would want to call this the aqueous phase. So aqueous phase, and then the DCM here we would call the organic phase. Okay, all right. And so since these two separate, another term you want to understand here is what's called miscibility, right? These two are what's called immiscible with one another, all right? Meaning they don't mix, all right? So oil and water doesn't mix. Those two are immiscible from one another. That's why you see two phases, all right? And so yet again, we're going to put our charged amine species. It's going to be in the water again, but remember partition coefficient, we can't just do this once. So what we're going to do is, now that this has happened in this step, we're going to separate these two, pour the DCM back in, and then add more acid so that we can keep pulling as much of that charged amine species out. Okay, and that's how you're going to separate them. Okay, now there are more steps incorporated into your procedure here, where you're going to actually, after you get them separated, we're going to call stuff like hydroxide extract. Okay, so what we're saying here for your hydroxide extract, remember in the first set when I showed you here, we took our mixture of three compounds. Let me come over here for a second. We took our mixture of all three compounds, we added the sodium hydroxide, and so here you had water, but remember you used sodium hydroxide, so this would be our hydroxide extract. So you have your charged acidic species here, All right, so don't get confused by seeing this hydride extract and think that, oh, that's my basic compound. No, that's your acidic compound. And so the thing is, so your carboxylic acid is negatively charged because it reacted with the base, hydroxide. And so what do? In order to separate it out from solution, you're going to react it with a strong acid, HCl, so that you can neutralize it. So what's going to wind up happening here in this scenario, in order to remove it from solution, you're going to have your charged carboxylic acid. All right, I'll put the Cl there, it doesn't really matter. But when you add the HCl, right, this is the conjugate base form of carboxylic acid. So it's going to act like a base. It's gonna one of the lone pairs on the oxygen are going to attack the hydrogen, and so you're going to get this neutral acidic species now, right? Your neutral carboxylic acid species. And so remember, this is very soluble in water, but this is not. So what's going to happen is you're going to see this white precipitate form, right? Precipitate form when you do this reaction. And so that's how you're separating them out. Now, in your final step of your separation, when you just have your biphenyl left in the DCM, this won't react with an acid or a base, and so the way you're going to remove that is you're going to use the rotovap, right? So this allows you to remove the solvent, remove the DCM based off of its volatility. And so it's going to remove the DCM, and you're just going to have a solid powder of your neutral compound left over in the rotovap. Okay, that should do it for the pre-lab. Good luck.